Well, I'm going to carry on towards the classification theorem. So I kind of need all that set up. There's a whole load of baggage that comes along with this subject. So G is a finite dimensional semi-simple Lie algebra. And I need a maximal toroidal subalgebra to be chosen. That defines a root system from the Carton decomposition. Then you need to pick a base, delta, alpha 1 through alpha L for that root system. And then you need to pick a basis. Like we did last time, we picked this kind of standard basis, E alpha, F alpha, is alpha arranged over the positive roots associated to that choice of base, and then the H alphas as alpha arranged over the simple roots. So that was that basis as fixed last time. And then you remember I write EI, HI, FI are E alpha I, H alpha I, and F alpha I. So these are the simple generators. And let me see, we showed last time that these SL2 triples, as I goes from 1 up to L, generate G as a Lie algebra. So as soon as you've got a nice set of generators for your Lie algebra, you wonder what are the relations that hold between those generators. And that's exactly what's going to be answered by the next extremely important theorem. So maybe the last piece of notation I need to let Cij be alpha I, alpha j check. So this matrix Cij, maybe I'll call that capital C, as I and j go from 1 up to L, is the Cartan matrix of that root system that we're looking at. So here's the all-important theorem, Serre's theorem. G is generated by those EI, HI, FI, as I goes from 1 to L, subject only to the following relations. This is for all I and j between 1 and L. So here are the relations. Well, the first one's pretty boring. HI and HJ commute for all I and j. The commutator of an EI and an FJ, well, there's a Kronecker delta. If I equals j, it's HI, and if I doesn't equal j, it's 0. They commute. Third relation is the commutator of HI and EJ. That's CJI, EJ, and similarly HI with FJ is minus CJI, FJ. And then there's two more relations, and it's best to use add here to write them down. Add EI to the power 1 minus CJI applied to EJ is 0, and similarly add FI to the power 1 minus CJI applied to FJ is 0. So these two guys are for I different from j. You need that because CII is a 2, so that would be a power minus 1 in there, which wouldn't make sense. But as soon as I is not equal to j, CJI is less than or equal to 0, so that power makes sense. So let me see, there's a few things to be said. So I'm going to maybe name these relations. S1, Serre 1, S2, Serre 2, Serre 3, and I'm going to call this thing Sij plus, and this thing Sij minus. So these are the Serre relations. And one thing you'll observe is they depend only on the Cartan matrix C. That's all that goes into this. You need to know the number L, which is the Cartan matrix is an L by L matrix, and you need to know the Cartan integers. That's the only data that you need to feed into this presentation. Another comment I should make here is that I'm following Humphreys. Definitions here, but actually the more recent literature, Humphreys was 1972, I think, but I think even in the mid-70s, I think people transposed this matrix. So that's something you've got to watch out for a little bit. So when you look at the Serre relation, they wouldn't be writing CJI there; they'd be writing CIJ, and it's kind of nicer that way, right? HIEJ is CIJEJ. I don't know. It just alphabetical order seems better, so I think that was why it got transposed at some point. But Humphreys uses this definition of the Cartan matrix. So more recently, the IJ entry of the Cartan matrix would be alpha I check alpha J. Okay, so there's Serre's theorem, and so I've got to talk a little bit about it. So note here, for the first time, we're talking about generators and relations. For Lie algebras. I haven't talked about this in any of the lectures. This requires the notion of the free Lie algebra. On a set, or on maybe a vector space whose basis is given by the elements of that set. So I haven't talked about this in the lectures, but I did talk about it on one of the homeworks. In homework 4, question 5, you'll see the construction of the free Lie algebra. So I'll just refer you to that. I think everything's pretty clear then. So the theorem, Serre's theorem, gives a presentation for Lie algebra. And as I observed, that these relations only depend on the Cartan matrix, so you could just call that matrix G of C. So it's got, so here it is. So this is what that means, right? A presentation. It means you take the free Lie algebra, so right there, that's the free Lie algebra on these generators. The EI, HI, and FI, and then you just quotient out by the ideal generated by S1, S2, S3, Sij plus, and Sij minus. Right, so I guess you do the usual thing you're used to. You instead of writing this as a relation equals 0, you just take this element. It's some successive bunch of EI commutators applied to EJ. So it's an element of that Lie algebra, the free Lie algebra, and you just take the ideal of the free Lie algebra generated by all of those elements corresponding to those relations. So this is just the ideal generated by the elements corresponding to the relations. So it's completely the usual thing you're familiar with giving presentations for associative algebras or whatever. It's just the same for Lie algebras. You just need this construction of the free Lie algebra to get started. So as well as Serre's theorem, there's a sort of another version of it, and actually this is where all the real work is going to do. I'm just going to call that Serre's theorem prime. So let me state that version of it. Let C be a Cartan matrix arising from a root system R. Then the Lie algebra G of C, defined by the Serre relations. So that's a Lie algebra I've just defined just straight above the theorem, is a finite dimensional semi-simple Lie algebra with maximal toroidal subalgebra T generated by H1 up to HL, root system R with simple roots alpha 1 up to alpha L corresponding to H1 up to HL. So those H's, those would be the co-roots, the alpha 1 check up to alpha L check under the isomorphism between T and T star, and Cartan matrix C alpha I alpha J check. So this presentation does in fact produce a semi-simple Lie algebra with exactly that root system. So let me see, I want to give some examples, because the hard thing here is just to kind of get familiar with these two difficult axioms. So I just want to give examples. Everything's kind of rank 2, so I really just need to think about some rank 2 examples. And I just want to just expand those relations. I guess we should start with A2. So this is the Lie algebra SL3 of C, and you know this Lie algebra. So this would be E1, and E2 would be that matrix. F1 and F2 would be the transposes. H1 would be the diagonal matrix 1 minus 1 0, and H2 would be the diagonal matrix 0 1 minus 1. Okay, so these would be the explicit elements, the EIs, FIs, and HIs chosen in that Lie algebra. And then the Serre relations, well, most of them you know, but so I'm just going to focus on these, on the hard ones. So they say that E1, E1, E2 is E2, E2, E1 is 0, and similarly for the Fs. And so I'm just writing down these relations Sij plus here. Okay, so in this case, the Cartan matrix is the A2 Cartan matrix, so it's this matrix 2 minus 1 minus 1 2. So the only interesting entries for us are these off-diagonal entries, which are minus 1. And this Serre relation was that add EI to the 1 minus CJI, EJ is 0. So I and J have to be 1 and 2. So this is a minus 1. So 1 minus minus it. So this is add EI squared, right? So that's what I've done here. I've done add E1, and then I've done add E1 again. So that's exactly add E1 squared. That's that relation. And this is add E2 squared. Okay, so there's the relation. It's sometimes if you're in the universal enveloping algebra, you often see this relation E1, E2 equals 0 turned into an associative algebra relation. In fact, if you take exactly the same relations here and you take them as defining relations for an associative algebra where the commutator means hi hj minus hj hi in the obvious way, that automatically gives you a presentation for the universal enveloping algebra of this Lie algebra. So you often see these Serre relations written in that setting for associative algebras. And so I thought I would just write out that relation. Here it is. If I don't use the Lie bracket, but I write it out in the associative way. So it's E1 E2 minus E2 E1 minus E1 E2 minus E2 E1 E1 equals 0. Okay, so I could, I guess, write it just for short. I could write 1, 1, 2. So this is just a shorthand. Instead of writing E1 squared E2, I'm just going to write 1, 1, 2. And then what else have I got? I've got a E1, E2, E1. So I'm going to write that as 1, 2, 1. But I've got another one of them there. So there's two lots of E1, E2, E1. And then finally there's an E1, E1, E2. So that's kind of my weird shorthand for that Serre relation written in this associative form. So let's see, that's just a sort of a way of remembering it, maybe. Let's look at maybe B2. So B2 is SO5. So the Cartan matrix for B2 is, let me get the one I want to do. Yeah, we're using this convention. So there's the Cartan matrix for B2. So from that, you see that the generators are E1, E2, H1, H2, F1, F2. It's a rank 2 root system. And the Serre relations are the add of E1 squared over E2. So this depends on the 2, 1 entry of the Cartan matrix, which is -1. So it's just exactly the same as in type A. In that case, it's a -1 in the Cartan entry. So that's 0. And the one that's more interesting is add E2 squared E1, because that's the 1, 2 entry of the Cartan matrix. So it's not squared. It's 1 minus the Cartan entry. It's cubed is 0. So this one starts to be a more interesting relation. You have to bracket with E2, and then bracket with E2 again, and then bracket with E2 again. That's the Serre relation. When Cji is -2. So it's, again, if I were to expand this in associative form, it gives you 2, 2, 2, 1. Then you get -3 lots of 2, 2, 1, 2, plus 3 lots of 2, 1, 2, 2, minus a 1, 2, 2, 2. That's my cryptic way of writing that. You obviously see Pascal's triangle coming in there. So if you were doing G2, the Cartan matrix for G2 is this guy. So there you would get add E1 to the 4th power of E2 is 0. And I guess the add E2 was just squared E1. So those would be the Serre relations. So the interesting one this time is this guy. So this is E1, E2, bracketed 4 times. So I've got to do it again. That's the second time, the third time, and then the 4th time, right? So it's kind of crazy writing the relation down like that. But my mnemonic is quite helpful for this. This is what I need. 1, 2, 3, 4 1s and a 2. 3 1s, a 2 and a 1. 2 1s, a 2 and 2 1s. 1, 2, 1, 1, 1. And then 2, 1, 1, 1, 1. And that's not quite going to fit here for me. There we go. And of course the coefficients, when you turn this into this associative algebra relation to get a presentation for the universal enveloping algebra, you get -4 plus 6 minus 4 in there. Okay. So that's just examples of this Serre presentation, just so you get a feeling for this Serre relation. Actually, it's kind of what's kind of most amusing with this is that you can take more general matrices. So when I'm using the word Cartan matrix, I mean Cartan matrix coming from a root system according to our classification of root systems. So one of these Cartan matrices coming from a Dinkin diagram, as we classified. But you can consider more general, what are called generalized Cartan matrices. Where all you require is that there's 2's on the diagonal, and on the off diagonal, the ij entry is negative, is less than or equal to 0, and it's non-zero if and only if the ji entry is non-zero. So whatever. It's a generalized Cartan matrix. This is actually the generalized Cartan matrix of type A1 hat. And you can write down the Serre presentation. It still makes sense. So you get a Lie algebra G of C of that Cartan matrix. What goes wrong when you don't have a genuine Cartan matrix of a root system, you still get a very interesting Lie algebra. It's called a Kac-Moody Lie algebra. It ceases to be finite dimensional, but it still has many of the nice properties of the finite dimensional semi-simple Lie algebra. So in this case, if you do A1 hat, you get this Lie algebra. I think I stuck it on one of the homeworks. You get essentially SL2 hat of C. Actually, you get the derived subalgebra of that. You don't have that derivation on top if you remember that homework. Okay, so anyway, that's just getting used to the relations in Serre's theorem, these relations. So let's see if we can. So what I'm going to do is I'm going to prove Serre's theorem, assuming Serre's theorem prime. Okay, so all the work gets pushed to this primed theorem, which is actually the one that analyzes these relations exactly, showing that the Lie algebra given by them is indeed a semi-simple Lie algebra of the right type. I'm gonna prove that theorem, I think, in lecture 9.3. But let's prove the first theorem. So the proof of Serre's theorem, and I'm going to prove it assuming Serre's theorem prime. Sorry, it's a bit cryptic today. I don't know why that happened. So for Serre's theorem, we're starting with G. We're starting with a given semi-simple Lie algebra. We've shown G is generated by the EI, HI, FIs. Let's check all the Serre relations hold. Okay, so let's check all of those relations. So Serre 1, that's just that HI, HJ is 0. That's kind of trivial because the maximal toral subalgebra is abelian. Serre 2. So I got to calculate the commutators of an EI and an FI. Well, we know they're in an SL2 triple, and that commutator is HI. And then I have to look at this one when I is not equal to J. But you see this element here, it lies in, you see EI is in the alpha I root space, FJ is in the minus alpha J root space, so it would be in that weight space, but that's 0, as alpha I minus alpha J is not a root. Okay, so that's that relation. Serre 3, that's just the one about HI, EJ. Well, EJ is in the alpha J root space, right? So that bracket, you get alpha J of HI, EJ. But that alpha J of HI, that's just alpha J, alpha I check, which is indeed the JI entry of the Cartan matrix, right? So that's just and similarly for F. Then I'm just going to do Sij plus, and Sij minus is similar. So this relation goes back to, I think it was lecture 7.2, lemma 3, where we looked at this alpha string through beta. So in this case, we were interested in the alpha I string through alpha j. So the way that went is we let R and Q be maximal, so that, let me see, alpha j minus R alpha I and alpha j plus Q alpha I are roots. And then we showed that R minus Q was alpha j of hi, right? So that's the Carton integer cji in the current notation. Oh, but actually, hang on. They're making this look much more complicated than it needs to, because actually R is 0, because already alpha j minus alpha I is not a root. We just observed that, right? So actually R is 0. So this is just telling us that this Q is minus Cji. And then this alpha I string through alpha j, it's at the bottom, it's alpha j and then alpha j plus alpha I and so on, and it ends at alpha j plus Q alpha I. And if you remember what was going on there, that was when we looked at the action of this SL2, the ith SL2. So we actually looked at the direct sum of all of these root spaces, alpha j plus n alpha I, and we looked at how that SL2, S of alpha I, acts. And we showed that it was an irreducible representation. And that was where this string came from in the first place. This was just a picture of this SL2 module. And so now we're in that situation that we've got this EJ, which is sitting inside that root space. So what we're doing is we're applying EI to it. So EJ is the lowest weight vector in that SL2 string, and each time we apply EI to it, we're moving it up the string. So to get to the top, we've got to apply EI to it minus CJI times. And if we apply it one more time, oh, that's in the wrong place. If we apply it one more time, we get 0. So that's where that relation comes from. This is just pushing you up that string, and we know everything about that string length from the Cartan matrix. Okay, so that checks that all the relations hold. And well, now you just do the standard thing, right? Now it follows that if we take the Lie algebra with that presentation, so that's that quotient of the free Lie algebra by those relations, by a universal property, there's a homomorphism sending EI, HI, and FI, the generators of the Lie algebra with that presentation, to the given EI, HI, and FI in G. Surjective because those guys generate, is well defined because we've checked that all the relations hold in G. And so finally you need to show that this is an isomorphism. It just remains to see that the dimension of our Lie algebra G is the dimension of the Lie algebra with these generators and relations. But we know that this guy here is just, what is it? It's the number of vectors in our basis, so it's the number of roots plus the number of simple roots. This follows. So we've got to see that the Lie algebra with this presentation has the same dimension, but this follows from the Serre theorem prime that I've given you, because that exactly shows that indeed this is a Lie algebra with the same root system. So it's got the Cartan decomposition exactly the same as G. So it has the same dimension. Okay, so that's just deducing the Serre theorem that I stated first of all from the actual one that we're going to have to work to prove in lecture 9.3, my Serre theorem prime. But I don't want to get bogged down in the proof of this. The proof of this, so this is now the main thing left to do. And it's quite tricky. It's quite a lengthy argument. So I don't want to get into that right now. Instead, what I want to do is I want to show you applications. Because they're rather striking, and that convinces you that this is worth the effort, this theorem. The primed one that we haven't proved yet, it's really an existence theorem. It shows that every root system is realized as the root system of some finite dimensional semi-simple Lie algebra. As well as that, I'm going to show you two more theorems which are consequences of Serre's theorem. But for them I need a lemma, and this is a slightly awkward lemma. But let's state it first of all. Let R and R prime be two root systems with bases. We're going to have delta as the basis for R. I'm going to call that alpha 1 up to alpha L. And delta prime is going to be alpha 1 prime. I guess it might be different rank, alpha L prime prime. Assume I need the Carton matrices as well. Let's put that in. You need bases and Carton matrices C and C prime. Too many primes. Assume that R and R prime are not isomorphic root systems. Then the semi-simple Lie algebras G of C and G of C prime defined by the Serre relations are not isomorphic. So this is a slightly awkward lemma because actually I'm going to defer kind of an important part of its proof to the future because it depends a little bit on knowing some representation theory, which we're not going to be able to develop in this course fully enough. Without loss of generality, you can assume that R and R prime are both indecomposable root systems. So we've got to show that if the Lie algebras G of C and G of C prime are isomorphic, then the root systems are isomorphic. Well, if the Lie algebras are isomorphic, remember that Serre's theorem prime says that G of C, it's got a Cartan decomposition that realizes the root system R. So the dimension of G of C, it's the size of R plus the size of delta, and because these are isomorphic, that's got to be the same as the dimension of G of C prime. Moreover, the dimension of the smallest irreducible, non-trivial, not the trivial module, G of C module is as listed in the table. So I need to give you this table. Well, it depends on what the root system is. So I'm going to write here this dimension of the smallest non-trivial irrep. And for good measure, I'm going to write size of R plus the size of delta. That's something that is the same for both G of C and G of C prime. Okay, so let's fill in this table a little bit. So it depends on the root system. We've got AL, BL, CL, DL, E6, E7, E8, F4, and G2. So let me fill in the last column to start with. So the rank is, so this is L squared plus 2L, this is 2L squared plus L, this is 2L squared plus L. For DL, it's 2L squared minus L. For E6, it turns out to be 78. We haven't played with these root systems. E7 is 133, E8 is 248, F4 is 52, and G2 is 14. Okay, so that's just something that depends on just constructing these root systems, then you can read off these numbers. Then I need the dimensions of the smallest non-trivial irreducible representation of this Lie algebra G of C constructed by Serre's theorem prime, and that's L plus 1 for AL. Of course, you kind of know that, right? This is SL, L plus 1 of C, and that smallest non-trivial irreducible representation is the natural representation of that Lie algebra. BL, it's 2L plus 1. This is the special orthogonal Lie algebra, the odd one, so this is exactly what you're expecting. This is SO 2L plus 1 of C, and that smallest dimension is that natural representation. CL is the symplectic Lie algebra with natural representation 2L. DL is the orthogonal one with natural representation of dimension 2L. And then the exceptional ones are maybe not so familiar: 56, 27, 56, 248, 26, and 7. So this is the thing that's a little bit awkward, because to get hold of this column, they follow from something called the Weyl dimension formula. Which is not going to be proved in this course. But it's the very next thing that you would want to do. You would want to develop the representation theory of semi-simple Lie algebras. We've already done the representation theory of SL2, and there's a kind of generalization of that setup for a general semi-simple Lie algebra. Actually, it just depends on knowing the Carton decomposition of your Lie algebra. So just the data that you have coming from the root system, you can then classify the finite dimensional irreducible representations and calculate all of their dimensions. This is what Weyl dimension formula does. And once you've got that, it's a total triviality to read off this number that's the smallest dimension. The point is, this is an invariant of the Lie algebra G of C. It doesn't depend on C, it just depends on that Lie algebra, the smallest non-trivial irreducible representation. So we've got these invariants, and our assumption that G of C is isomorphic to G of C prime will mean that these invariants for G of C are going to be equal to the ones for G of C prime. So this dimension is the same as for G of C prime, and it remains to note that these two invariants determine the isomorphism type of the root system R uniquely, and so that is all we need to finish the proof of the lemma. Right, so that's the point, is that on all of the root systems here, these two invariants, they just distinguish them all. There are no coincidences. Remember, AL starts at L greater than or equal to 1, BL L greater than or equal to 2, CL is L greater than or equal to 3, and DL is L greater than or equal to 4. Okay, so that proves that lemma, that awkward lemma, because it's something I'm not going to give you the Weyl dimension formula at this point, so it's sort of pushed to the future. But the proof of that Weyl dimension formula just depends on knowing G of C together with its Cartan decomposition and its root datum. It doesn't depend in any way on the theorems I'm about to write down that use this lemma. Okay, great. So that's the awkward lemma. So now I can prove the conjugacy theorem. That G be a finite dimensional semi-simple Lie algebra, then all maximal Tyrrell subalgebras of G are conjugate under automorphisms. Of G. In particular, they all have the same dimension. That's this rank that I'm denoting L. So it shows that rank is well defined for a finite dimensional semi-simple Lie algebras. Okay, so the proof uses. So maybe I better pick 2. There'll be 2 maximal Tyrrell subalgebras. Of G. So from T you get a Cartan decomposition, so you get a root system. From T prime you get a different Cartan decomposition, you get a different root system. And then you do the usual thing that we do for a root system. You pick a base and you get the Cartan matrix. For R prime you pick a base and you get the Cartan matrix. Serre's theorem shows that G is isomorphic to the Lie algebra given by Serre's presentation from the Cartan matrix C. That's applying Serre's theorem once with this choice of T, and then you apply it again to this choice of T, and you get another isomorphism between G and the Lie algebra with the presentation coming from that other Cartan matrix. And this isomorphism, we know it takes T to the span of H1 up to HL, the span of the H's in the presentation for G of C, and it takes T to the span of, I'm going to write H1 prime, hopefully my notation is clear, HL prime prime, the span of the H part of the Serre presentation for G of C prime. Okay, so that is a maximal Tyrrell subalgebra of G of C, that's the maximal Tyrrell subalgebra of G of C prime coming from the presentation. And these isomorphisms from Serre's theorem, they take the given T here, or the given T prime here, to the maximal Tyrrell subalgebra from Serre's presentation. But hang on, by the lemma, you see G of C is isomorphic to G, which is isomorphic to G of C prime. So the lemma shows that R and R prime, the two root systems, are isomorphic. And now all you have to do is you have to pick an isomorphism, R to R prime, taking delta to delta prime, which you can do as all bases are conjugate under the Weyl group. And conjugating with the Weyl group is an automorphism of your root system. So you can pick an isomorphism from these between these two root systems, which takes the base to the base. And then this just obviously induces an isomorphism from the Lie algebras with these presentations, G of C and G of C prime. Remember, the presentation just depends on the Cartan matrix. So we've kind of matched up the bases in this way. and the corresponding Cartan matrices will match up. That'll just give you a bijection between the rows and columns of those Cartan matrices. And so the Lie algebras here, they've just got exactly the same presentation. But this isomorphism will take H1 up to HL, to H1 prime up to HL prime. So that's what I've got right here. I've got this isomorphism right here. And now all you have to do is apply that map, and that map. That composite gives an automorphism of G taking T to T prime, and that's what you want, right? So this sends T to there, that goes to the Cartan of G of C prime, and that backward map takes you back to T prime. So we've constructed an automorphism of G which takes T to T prime. There's the conjugacy theorem. Okay, so my proof of the conjugacy theorem, it depended crucially on this lemma, because I needed to know that if G of C was isomorphic to G of C prime, then R was isomorphic to R prime. But if you, indeed in Humphreys, he gives a direct proof of the conjugacy theorem which doesn't invoke the Serre presentation or this stuff from representation theory. It's a bit of a lengthy proof, so I've shown you a way that's kind of avoids it. The representation theory needs to be developed anyway, so this proof is actually cheaper. But if we could prove this conjugacy theorem directly, then I wouldn't need that representation theoretic lemma that I've just assumed in the proof I've shown you. Okay, so that's the conjugacy theorem, and then the final theorem is the isomorphism theorem. So it asserts that there's a bijection from finite dimensional semi-simple Lie algebras that set up to isomorphism and root systems up to isomorphism. So there's in fact not just one bijection, there's mutually inverse bijections. There's a forward and a reverse bijection. In the forward direction, you take a finite dimensional semi-simple Lie algebra G, you pick a maximal Toral subalgebra, T, and then you let R be the corresponding root system. That arises from the Cartan decomposition. Of G with respect to T. This is well defined independent of the choice of that maximal Toral subalgebra due to the conjugacy theorem. If you make a different choice of T, well, the conjugacy theorem says that's just changing, there's an automorphism taking T to T prime, so actually the root system doesn't depend up to isomorphism on the choice that you made. So that's the forward map, and in the reverse direction, you just take a base, delta for R, hence you get a Cartan matrix, and then you send R to the semi-simple Lie algebra G of C, which is a finite dimensional semi-simple Lie algebra using Serre's theorem prime. Okay, and then finally you've got to check that that's the identity And that's the identity, but this just follows from the Serre theorem and the prime version. And so the Serre theorem says that if you start with G and you find this root system, so that's going in this direction, and then you get a Carton matrix, that then G of C is isomorphic to the G you started with, right? So this is exactly Serre's theorem, and this being the identity, well, that's exactly Serre's theorem prime. So that's the proof of the isomorphism theorem. I guess the proof is right here. So it's all about the construction and getting that this forward map is well defined, and then Serre's theorem does the job. Okay, so that completes the classification of finite dimensional semi-simple Lie algebras. They're classified by their root systems or their Dynkin diagrams is a nicer way to think about it. But we've got a little bit of work to do. We are this lemma which depended on the Weyl dimension formula, well, that's pushed to the future when you study representation theory of these semi-simple Lie algebras in terms of the combinatorial data of root systems. But we've still got to prove Serre's theorem prime, and I'm going to do that in the next lecture. It's a bit of a technical proof, but I'll go through the main steps.